We have discussed composition of forces in earlier modules. The process yields a net resultant and initiate motion as per the magnitude and direction of the same. What happens when the resultant force is zero? Yes, the object will be in equilibrium. Is that the only condition for equilibrium? This brief module provides a quick insight into the conditions of equilibrium for different systems of forces. Application of Lami's theorem for specific cases of concurrent forces are also explained. These can be conveniently utilized for evaluating unknown parameters during analysis of equilibrium conditions. So, let's begin. For collinear forces, resultant is the algebraic sum of individual forces. So, sigma F equal to 0 is the condition for equilibrium for collinear forces. We have seen that concurrent forces in different orientations can be transformed into a set of collinear forces in the horizontal and vertical directions. Hence, a set of concurrent forces will be in equilibrium when the net force in both the directions are 0. That is, sigma Fx equal to 0 and sigma Fy equal to 0 are the conditions of equilibrium for concurrent forces. Earlier, we have discussed graphical methods of composition of forces. While using graphical methods, how do we understand that a concurrent system of forces is in equilibrium? Let us find out the resultant using polygon law of forces. Yes, the forces form a closed loop. As per the polygon law, the distance from the start point to end point defines the magnitude of the resultant. So a closed loop indicates zero resultant and is in equilibrium. Now let us move on to non-concurrent system of forces. Simply satisfying sigma Fx equal to 0 and sigma Fy equal to 0 do not ensure equilibrium of non-concurrent forces. Let us try to understand the same with simple examples. The beam is subjected to 4 10 Newton forces in the vertical direction, 2 of them in the upward direction and the other 2 downwards. There are no horizontal loads present, and it is clear that the net force in the vertical direction is 0. So the system is satisfying sigma Fx equal to 0 and sigma Fy equal to 0. Is the system in equilibrium? We can see that two force couples having same magnitude and direction are acting on the system. The moment of couple initiate a rotational effect and the system will not be in equilibrium. Detailed information on couple and its impact on the system are covered in a separate video. Let us evaluate the moment of forces about an assumed location, say the edge O of the beam. Sigma m is equal to minus 10 times 1 plus 10 times 2 minus 10 times 3 plus 10 times 4, which is equal to 20 Newton meter. Here, the clockwise moment is considered as positive and anti-clockwise moment is considered as negative. So, with respect to the moment center O, a net clockwise moment of 20 Newton meter will be acting on the system. This will initiate a clockwise rotation and the beam will not be in equilibrium. Now, let us reverse the direction of two of the forces. Again, the net force in the horizontal and vertical direction will be 0. The net moment with respect to moment center O will be sigma m is equal to minus 10 times 1 plus 10 times 2 plus 10 times 3 minus 10 times 4, which is equal to 0. For this system of forces, the net moment is also 0 and will not experience any rotational effect. So, for equilibrium, non-concurrent system of forces have to satisfy all the three equations simultaneously. That is sigma Fx equal to 0, sigma Fy equal to 0 and sigma m equal to 0. Moment can be estimated with respect to any convenient reference location. For collinear forces and concurrent forces, line of action of all the component forces are passing through a common point, and so the moment generated will be 0. So these three equations can be considered as conditions of equilibrium in general. However, a special case of equilibrium condition of coplanar concurrent forces involving only three forces, Lami's theorem can also be utilized. As per Lami's theorem, each force is proportional to the sine of the angle between the other two. So for coplanar concurrent system involving only three forces, F1 divided by sine theta 1 is equal to F2 divided by sine theta 2, which is same as F3 divided by sine theta 3. Generally, analysis of three coplanar concurrent forces in equilibrium will be much easier when we follow Lami's theorem. The equations of equilibrium, as explained in this video, can be conveniently utilized for estimating unknown parameters. The primary step while evaluating a system in equilibrium is preparation of free body diagrams. Numerical sample problems demonstrating application of conditions of equilibrium, free body diagrams, and analysis of systems are covered in separate videos. Hope this content was helpful in getting a quick overview of the topic. If you have comments, feel free to share them in the comment box. If you found this video informative, please give it a thumbs up and consider subscribing to stay updated on future episodes. Thanks for watching.